Lesson 1.4, geometric series. So up to this point, we've talked about arithmetic sequences, arithmetic series, and geometric sequences. Today, we're kind of combining the two, and we are talking about a geometric series. So geometric meaning that we're multiplying instead of adding or subtracting. Series meaning that we are going to be totaling up the numbers in the sequence. So I'll let you pause before you even get started and complete the pattern and the table on the following page. So finish iterations 4 and 5 and then complete the table below it. And on this, in your case, it's going to be on the next page. As you can see, I've also completed these iterations and I've completed the table below. What do we notice about these values? Well, 1 to 2 is multiplied by 2, 2 to 4 is also multiplied by 2, 4 to 8 is multiplied by 2. And so we could say that our common ratio is 2. If we can define a common ratio, then we can definitely conclude that a geometric sequence has occurred. Another way of deciding is just by looking and saying, well, it's always multiplying by 2. So our first term, first of all, yes, it is a geometric sequence. Term 1 is always your very first value, so 1. We're going by the number of new branches. My common ratio, or R, is going to be 2. And my general term, I need to actually write by using my equation. So it's totally okay if you don't remember this from the previous day, because you just learned it, and maybe it wasn't the previous day, maybe you've taken a couple days off. So we've got term 1 multiplied by your common ratio to the power of n minus 1. In our case, this is going to be term n, because it's still a general term, equals 1, or we don't even need to write it. It's just 2 to the power of n minus 1. Find and describe a strategy you could use to determine the total number of branches formed by the end of 5 iterations. So you could do this any number of ways. There are so many different options you could choose. The easiest or most straightforward and obvious choice would be to actually determine the first 5 iterations like we have. Adding these 5 iterations is entirely practical, but as this question number 3 suggests, adding up to the first 100 iterations might be a little insane. So instead, we need an equation. So in our example above, to find the total number of branches on the fractal tree, that is a geometric series. So it's a sum of the terms of the geometric sequence. For example, 6, 12, 24, 48 is a geometric sequence. Constantly doing what? Doubling as well. It's our most common geometric sequence. Okay, and so our geometric series for this would be 6 plus 12 plus 24 plus 48 plus the numbers that follow. So the geometric series above, if I just wanted to talk about the series of one value, then it would just be term 1. So this series of term 1 would just be 6. But the series of 2 values would be term 1 and term 2 added together. So that would be 6 plus 12, which would be 18. If we continue, for 3 values, or 3 terms, it would be 6 plus 12 plus 24. So that could also be looked at as 18 plus 24. So that is 42. As you can see, again, we're getting into really big numbers, just like we did with our arithmetic sequences and their series. So we want that equation as soon as humanly possible. So in general, we can write this as term 1 plus solving for term 2, solving for term 3, all the way up to solving for term n, all written in the context of term 1. We can simplify this even further because term 1 is showing up in every single one of these terms of the equation. So we can factor that out and we look at what's still left behind, and we're left with 1 minus r to the power of n, all divided by 1 subtract r. Now remember that r cannot be 1 in this case because, anyone guess why? Our denominator. 1 subtract 1 is 0. Nothing can be divided by 0. So r must not be 1. So our geometric series cannot be all the same number. So before we had said r can't be 0, now r cannot be 1 either. So this is our big equation. Again, you're going to want to make note of this because we're going to be using it a lot. Term 1, just like before, is first term. R is our common ratio. Sn is the sum of the first n terms in our sequence. And n is the number of terms. And n must be a positive integer. So this is something that we haven't talked that much about yet. Positive integer. So n cannot be negative. It also cannot be a decimal. Okay? Because you can't have part way between 2 terms, because that would mean that there's something else there and you're no longer talking about term 1 and term 2 and term 1.5. Term 1.5 would have been term 2, and that changes our sequence. So watch out for that. So look at example 1 and try and apply this equation that we have. So determine the sum of the first 12 terms for this geometric series. So we are trying to figure out the sum of 12 terms. That's what we're trying to figure out. So Sn is going to be S12. The geometric series is 3 plus 12 plus 48 plus 192, etc. So term 1 is going to be 3. R is going to be 12 divided by 3, which is 4. Remember, I said not to stack like that. Well, I'm not sure what's going on here. So we're going to erase that. 4. And that's all the information we need, because by filling in our Sn is S12, we know that n is 12. So again, write down your equation, get in that habit. plug in. So we're looking for S12 again. Term 1 is 3, 1 minus 4 to the power of 12, all divided by 1 minus 12. No, 1 minus 12. 1 minus 4. Oh my goodness. Calculators are definitely going to be a necessity here because 4 to the power of 12 is going to be a large number. We can simplify it a little bit. 3 multiplied by 1 minus 4 to the power of 12 is, oh my goodness, 1, 6, 7, 7, 7, 2, 1, 6. Holy smokes. 16,777,216, all divided by -3. So again, that whole piece where I like to do as much mental math as I can, 3 divided by -3 is going to be -1. So those can simplify. And then I'm going to subtract 1 by that massive millions of number, and we're going to be left over with -16,777,215. A negative times a negative is a positive, so my final answer for the sum of the first 12 terms is going to be 16,777,215. Now, I don't know about you, but I wouldn't have wanted to figure that out without this equation. So example 2, the sum of the first 14 terms of a geometric series is 16,383. The common ratio is -2. Determine the first term. So again, we start with Sn equals term 1 multiplied by 1 minus r to the power of n, all divided by 1 minus r. We can pause to identify our variables. We're talking about the sum of the first 14 terms, so Sn is actually going to be S14, which means that n is 14. We're told that the common ratio is -2, but we also are actually told that not only is it S14, but we're told what that sum actually is, which is 16,383. And then we're asked to find term 1. Plug and chug is the next step once we have all our variables in our equation. Term 1 remains as it is. You can represent it with an x if you want it to do that. You would write that in place of that question mark, but I'm not going to. I'm going to keep it as term 1 because I find that if I leave it as the variable that it's supposed to represent, it just helps me remember what I was actually solving for. 1 subtract -2 to the power of 14. And this is why we put brackets around everything we substitute in. 1 subtract -2, because those negatives are going to have different impacts here. 16,383. Term 1, I'm going to simplify a little bit here. 1 subtract -2 to the power of 14 is 16,384. And remember, subtracting a negative is the same as adding a positive, so this is going to be all divided by 3. I can get rid of that 3 in the denominator right now, and the faster I can get rid of denominators, the better. Now I have term 1. I'm also going to simplify the brackets at the same time. I'm going to be left with a negative 16,383. And I've got 3 multiplied by 16,383. Now you can plug that into your calculator, but again, I like doing mental math as much as possible. And I notice that this number here, 1683, is showing up on both sides, and it's multiplying on the right. Granted, there's a negative in there, but I can move that at the same time. So I'm going to leave this as 3 multiplied by 16,383, and you'll see why in 2 seconds here. So I'm going to have to divide the right-hand side by negative 16,383. And if I do that to the right, I do that to the left, 16,383. These completely cancel out. Now I've got a negative in here, and a positive divided by a negative is a negative, so I know my value is going to be negative in the end. But now I've got 16,383 divided by 16,383. Well, any number divided by itself is 1. So they cancel out. I keep that negative. I treat it like it's negative 1 in the denominator there. And all I'm left with is a 3. And so term 1 must be negative 3. And that's my final answer. So by taking that little step of actually not multiplying, it saved me having to go back to my calculator again. So that's where there are some shortcuts to mental math. You just have to know what to watch for, looking for things that are in common that are going to cancel out, and canceling them out as soon as possible can be really advantageous. Here we go. A little bit more challenging now. Here we have the sum of the geometric series that we're trying to find, but we need to figure out what we're missing. So if we were figuring out our sum of our geometric series, we would use our handy dandy equation, 1 minus r to the power of n over 1 minus r. And we would need to know the following variables. Sn is what we're solving for. Term 1, we are given, it's negative 3. R, we are not given, but we could figure out. But also, we do not know our n value, and so we're going to have to solve for that. So we're going to have to solve for both r and n. R is relatively easy. Remember that to solve for r, our common ratio, we take the later term divided by the previous term. So we've got negative 15 divided by negative 3. So r is positive 5. I'm just going to keep a running list over here on the right of all these variables that I've had to solve for. Now, n's going to be a little bit trickier. This is actually where we're going to have to go back to our previous lesson again and figure out n. So we have our last term. We do know it. So when we go to plug in to the equation, Tn equals T1 r to the power of n minus 1, we do know term n. We know its value. We don't know what n is, but we know that when we get there, whatever term it is, it's going to equal negative 46,875. So we can fill that part in. We do also have the ability to plug in term 1. R, we do know now. We just solved for it. 5. to the power of n minus 1. So we want to get that -3 out of here as quickly as possible. So that's the first thing I'm going to do, is divide by -3 on both sides. So 46,875 divided by 3 gives me a much smaller number of 15,625. From there, we need to figure out 5 to the power of what is equal to 15,625. So you're going to have to take a second, punch 15,625 into your calculator, divided by 5, and you're going to have to keep doing that. Now, if you hit the equal sign or the enter button over and over again, it should repeatedly do that math for you without you having to always type in divided by 5 until you get the right answer. So pause this video, do the work, grab your calculator, divide by 5 until you get an answer of not 5, but 1, because that means that we've got all the way down to 0 as our exponent. Now, don't lose count as you keep doing this, because there's going to be at least a few 5s that go into 15,625. Luckily, I've already done this, and I know that 5 to the power of 6 is equal to 15,625. So I can write that in its place. All right, 5 to the n minus 1. Well, if I've got a common base, I can say that 6 then has to equal n minus 1. So n is going to be, add 1 on both sides, cancel it out and move it away. We're going to get n equals 7. Once we've done this, then we are ready to go. We know everything except for our actual sum, and that is what the question is asking for. So we can plug and chug. So Sn equals -3 multiplied by 1 minus 5 to the power of 7. Again, 5 should be in brackets. Divided by 1 minus r, which is 5. Okay, so simplifying, we've got -3, 1, subtract 5 to the power of 7, which is 78,125 over -4. Now again, watching out, we've got negative, and a negative is a positive, so we can treat it like 3 multiplying by this and divided by +4 if we want. That's completely up to you. You could leave them as negatives as well. I just like getting rid of them if I can as early as possible, because that means that I'm less likely to forget them in the end. In brackets, I'm left with -78,124. At this point, I am definitely using a calculator. $58,593, and that is S7. And again, that's because this is the 7th term, based on what we did over here on the left. Example 4. A person takes tablets to cure a chest infection. Each tablet contains 500 milligrams of an antibiotic. About 15% of the mass of the antibiotic remains in the body when the next tablet is taken. Determine the mass of antibiotic in the body after each number of tablets. What kind of information do we have? always start with that. I'm going to pick out 500. Maybe I'm going to even include the milligrams because it's a word problem. 15% remains, so that means that's all that's left. And in our particular example for part A, we're looking at 3 tablets. What kind of information does this give us? Well, 500 is how much we're starting with, because we can't start with 0, because if we started with 0, 0 multiplied by anything is still 0. So we've got 500 is term 1. 15% is going to be our common ratio. But remember, like before, percents are actually out of 100, so we're going to write this as hundredths, which is 15. This is going to tell us that we are going to finish and find the sum of the first 3 terms. So again, make sure you have your equation somewhere handy, and you can start plugging in. So the sum of the first 3 tablets is going to be 500 plus, we've got 1 minus 0.15 to the power of 3, all divided by 1 minus 0.15. From there, we plug in chug. So we've got 500, 1 subtract 0.15 to the power of 0.003375. Again, you don't have to write down all these individual steps. We've got 0.85. Then you can calculate from here. 0.99665. Keep as many decimals as you can while you are doing this math. Finally, plug all this in together, multiply 500 by your decimal, and then divide it by 0.85, and that gives you 586.25. Now we just need to double check that we have in fact answered the question, the mass of antibiotic in the body after each number of tablets. So if I've taken 3 tablets, it makes sense that I've got over 500 because that last tablet I took still at 500. So in this sense, this geometric sequence is a little strange because we're constantly adding on to the end, but in a different way. Our most recent tablet that we've taken actually is always representing that term 1. Don't forget your units since this is a word problem, so it's milligrams, and that is the mass in your body of 3 tablets. 10 tablets, exact same procedure, so I'm going to do it a little bit quicker here. So we've got S10 equals 500 is term 1. 1 subtract 0.15 to the power of 10, all divided by 1 subtracted by 0.5. If I plug this into my calculator, 500 multiplied by 1 subtract 0.15 power of 10. If you are going to try and punch it in all at the same time, a key thing to watch out for is that you make sure your brackets are all in a line, and it should look very, very similar to how it's written on the page. In this case, I get 588.234 milligrams. So it's kind of crazy. If you take 10 tablets, you do not actually have that much more than if you take 3 tablets. Just some perspective there. Kind of crazy. And that's our last example. So now you are going to go back to that inside cover of your notes booklet that you've just been working through, and you're going to find out where in your workbook you're supposed to be doing, or you're going to turn to the next page in this little notes booklet and you're going to find some extra practice.